Okay, so PET connectomics. Okay, it's a strange combination if you want, because if you are a PET person, so it's strange to link PET with the connectivity, and probably if you work a lot with the connectivity stuff, it's strange to see PET in this environment. I want to demonstrate to you that it's quite interesting to have also this vision of PET inside this area. So first, we know that brain is, normally we say brain is a complex network. And normally we use, at least a lot of people use EEG or electrophysiological stuff and neuroimaging, particularly fMRI, to describe the network. But if you go in the past, so the first attempt to describe the PET as network was made by using EEG. That's because this is the history of the development of technologies that we already use. Of course, the first was EEG, so the first attempt to describe the brain as network was using EEG, and the second one was by using PET. In particular, the first year is highlighted in 1984. In particular, Horvitz published a paper regarding, again, so the vision of the brain as a network, but described by PET. And we have also to wait the second, important paper that was Friston defining the PET connectivity. It was already based on PET data. And also the definition of facial connectivity is based on PET data, of the vision of the PET data. The definition that we already use is based on PET. So here is just to highlight the two different papers, because also we will see that we will use them to describe the two different types of connectivity that are possible to keep, to measure by using PET. So the first is already, I've already described you, is the paper of Horvitz, and here he used 59 regions to describe the network and investigating the relationship between, for instance, the primary sensomotor and the primary sensomotor and the premotor areas and additional areas. So the scheme is quite simple because it's this one. So this is okay. This is what is the functional connectivity map at the time, but the meaning is exactly this one. So the way to investigate is a possible way to investigate the network. The second is it's a well-known paper by Princeton, and here it's interesting to is PET-based, is O15 water data. And still here there is the definition of functional connectivity as correlation of time curves, time activity curves of signals. Okay. So, okay, this is the past. We can say about we have fMRI now. We have a lot of course, interesting and important results, and fMRI provided and provide us a lot of information and interesting information describing the network and so on, and together with EEG. So really, this was the past. The past at the time where was the PET. Now we have something else that is cheaper, of course, is faster, and also it's not necessary to use radio tracers like in PET. So it's more safe. So why to be back? Why to introduce PET again in this connectomic vision of the brain? So there is a simple reason, because the brain is a complex network. It's a combination of biochemical and electrical processes. So it's unbelievable that we are able to understand really the complexity of the brain just only using EEG or just only fMRI. Of course, we can retrieve a lot of important knowledge from them, but it's not enough. It's not enough, in particular, to understand the link between healthy control and pathology. From my point of view, I think also for a lot of our researchers working in this multimodal area. So PET is able to give us a very important, detailed physiological information. We can investigate just only the blood flow, okay, but we can do it with also MR, but we can investigate the metabolism locally, and we'll see also as a network. I try to demonstrate use also as network. Of course, we can investigate the neuroreceptor systems throughout a lot of different types of tracers. We have more than 200 different tracers, in fact. It's different substances that we can investigate, really detailed information. So, okay, so I think we need to add this information inside the connectome. And okay, so we have a direct link throughout PET to the biological meaning, of course. The reproducibility of a PET study is very high. The ICC is between 0.8 to 0.9, also higher. It depends on the tracer, but it's very high. And okay, but what about the time? What about the voxel size? So normally the picture is this one that is highlighted here. We have a structural and diffusion information. The size is between 1 and 2 millimeters. So I speak about narrow imaging, so I speak about voxels and dimension of voxels. And after fMRI, 3 and 4 and so on. In true, of course, this is something called division, because PET, as MR scanners, we have a new scanner, the 7-taras scanner, or in any case also the 3-taras with a higher, for instance, diffusion gradient. So there is an improvement of the possibility, but also the technology for PET was not. It's not remaining at in 20 years ago, but we have a new PET scanners, and now from 4 we have a possibility with a Neuroexplorer, for instance, to reach a 1.5 millimeter isovoxel. So it's better than a common 3-taras fMRI. So it's not really a problem, you know. Of course, you have to have the right technology. And okay, but the time is different. Okay, but also the sampling time between EEG and fMRI is different because the process is different. Also in PET, there is the same meaning. The process is different. The sampling time is different. So it's lower because the process is slower. And so we can also a little bit discuss. Okay, so telling this, I think this is the scenario for the future. Having the possibility to describe the structural information as, you know, to investigate the network from a structural point of view, from a functional point of view, EEG, fMRI, but also from a, you know, molecular point of view. This is, so having the possibility to investigate by using glucose, investigating using for instance, dopamine, serotonin, and so on. And also, of course, to add not only to add also the directions, because this is a quite interesting information to add to the connectomics. So I think this will be is incoming. You know, really in a few years we will have this type of vision, this type of maps. So now I'm dealing with among all the possibilities that we have in PET, a lot of work is now focused on the glucose. So, and glucose for PET is FDG. FDG is the name of a tracer, and the result is something related, is a quantitative vision of a metabolic process. So it means that I can identify, for instance, the KI. KI is a measure with a is an absolute measure of the glucose consumption, voxel by voxel, of course, in gray as well as in white matter. Okay, so I'm going to introduce you the FDG. There is a sort of a renaissance of FDG because it was the most used tracer in the 80s, 90s. After we had the neurotransmitter area, now we have again a renaissance of FDG. So, which type of connectivity we can have? So, of course, PET, we can, I'm not going to introduce the use PET as a quantitative measure. So, the usual vision of PET as connectivity. So, how many PET connectivity we can use? We have 2 different types of connectivity, and mainly are coming from the 2 different articles that I provide you as the second slide of my presentation. The first linked to Horvitz, and the second linked to Freestone. This one is linked to the Horvitz. And we can have just only, for instance, this vision, this idea. So we have here is subjects, okay? So we have two regions, for instance, hippocampus and thalamus, and we are just sampling the values for a subject 1 of the glucose value in the first region and the glucose value in the second region. And so we can do subject by subject, and we can generate this type of plot and again provide a correlation between them. And this is the measure used by Horowitz in the first attempt to introduce the PET as a measure of a network connectivity. So this is called molecular connectivity covariance, and it's different from the meaning of partial connectivity provided by Christon, because it's not time-based, it's subject-based. However, we have several results. If you go inside the literature, you can find several results, and these are just only enough results to have review papers. These are just only, this is one, we have a second one, and also I highlighted just the last results concerning neurodegenerative disease, and using this PET connectivity, this molecular connectivity covariance as biomarker in order to investigate, to detect the regions that are affected by the disease, considering the response to the metabolic response. Okay, this is a possibility. Second possibility is this one. Here we have a time. We have just only one subject. We have the same regions, but now we have a signal, the PET signal, what we call time activity curves. Okay, and okay, it's not correlation is not the best measure to use here, because if you want a really good map, really red map, if you with values between 0.9 and 1, okay, this is a good way. Of course, the signal is different, so we have to find a different way to provide. There is a functional link, functional meaning, as Princeton defined the functional connectivity between these two curves. And there are, at this moment, 3 methods. One is was used by Tomasi, was ICA based. The second one is a seed-based correlation. The last one are based, of course, is a correlation, but with normalization. Normalization is a big issue in PET, because to normalize we need a reference region. A reference region is really an open question in every PET study. It's not so simple to define a correlation, and we know that if you change the normalization factor, you modify also the network. So it's a simple measure, but the normalization is quite a critical step. So, sorry, again, sorry. Okay, so just to summarize, we have 2 different types of visions, and I'm going to follow the second one. So based on the time, we use of the time, the vision of the time. And so I'm wrong the next time. So we need first to have a dynamic PET acquisition. And this is not simple, because normally if you go inside the data sets, also provided in sometimes also in OpenNeuro, but you can find, it's easy to find static PET. It's not so easy to find dynamic PET acquisition. It is, it's possible. And dynamic PET data, and we can derive, of course, the time to the curve, so the signals from this time period data, and we are able, so I will show, or by using CA or by using seed-based, I will show you a different way to have a map like this one, really closer to a functional map, if you want, not exactly the same, but overlapping with it, subject by subject. Of course, in the previous method is not suitable for subject-by-subject production. This type of map is a group level, just only giving you a map at a group level. This is possible to have. Okay, PET connectivity, in this case, is the measure was not correlation, but Euclidean similarity. We don't need any normalization. We publish this. And we can apply on different type of atlases, of course, as well as, of course, we can provide something in a more detailed atlas. Okay, the structure is a homotopic structure. It has small world network properties. So there is a relation between structural connectivity and functional connectivity. The relation is quite good. Sometimes it's also, sometimes it depends, of course, of the data set. In any case, it's similar to 0.4. So it's a good correlation. So if you think of the correlation between structural, when I say structure, I say diffusion-based structural connectivity maps and functional connectivity. More or less is the same, 0.4, 0.38, and depends on the data set. So the link is good, really good. So the first was to understand if, okay, we can provide map, but this method is sensitive to the pathology, because we wanted to propose this also as a way to link healthy network with a pathological network. And we used the glioma dataset that was applied with the team also Professor Corbetta, and some results are coming from the same dataset also that you already have seen. In many cases, we try to understand if it's possible to detect alteration in the metabolic connectivity, as well as we already have seen that it's possible with functional connectivity and structural connectivity. And we demonstrate that yes, it's possible. So here, SUVR means just only the local information. We see just only a local alteration of the SUVR of glucose consumption. So here I see in this voxel, I see that the glucose consumption is lower. And in green, you see the areas impacted by the lesion and related to this, a lower local metabolism. In orange, you see the areas that are impacted by the lesion, but considering metabolic connectivity, so the network that described by using FDG, by using the glucose information. And here, in pink, you have the regions impacted by, of course, local information, as well as network-based metabolic connectivity information. So there is an overlap also here, but also there is an additional information that is provided by looking the pathological impact of a lesion on the brain, not only locally, SUVR, but also considering the connectivity, the network, the way to communicate, to transmit the energy between the networks. So also here you can see that some networks are more impacted by metabolic connectivity, while there are other networks that are more impacted by local impairment of glucose. So, okay, so this is a sensitivity to pathology, and but we wanted to investigate it. We wanted to learn a little bit more, also in the healthy subject, considering this metabolic connectivity map. And we can go inside. So this is a paper published by Riddle in 2016, really interesting. There is a lot of different stuff. He used two different path dynamic acquisition, one with eyes open and another one with eyes closed. And he demonstrated an increase in local metabolism, that an increase in local metabolism reflects an increase in afferent links from source origin. Source, he is linking source, so directions, with metabolic level, metabolic consumption, okay, by using two different type of PET dynamic acquisition. And he demonstrated also that there is a comparing simple, I close and I open condition in healthy subject. Metabolic connectivity reveals stable bidirectional signaling among visual cortices and top-down signaling from parietal control regions. In addition to top-down signaling from the salience network occurs only during the eye open condition. So, of course, it's interesting. Of course, I suggest you to read it, but mainly, if you wanted just to summarize, there is a relationship between directions and glucose consumption. Okay, so what we can do, we don't have two different, so it's quite demanding to use to acquire two different PET dynamic scan in the same subject and so on. We can try to, link two different types of information, try to understand the combination between what is telling us from fMRI and what glucose is giving us as information. So in this case, we link the functional activity as described by HIBALL with glucose metabolism by using two different types of methods. In particular, we use for fMRI hepatic connectivity vision. So hepatic connectivity, I don't know if you know, or I'm sure that you know, but just to highlight, is a functional connectivity with, if I wanted to simplify, functional connectivity plus directions. Okay. And we are able to perform dynamic causal modeling, to apply dynamic causal modeling at whole brain level by using sparse DCM, was developed here in collaboration with Professor Chiuso in my department. And we are able now to have effective connectivity. So it's not only the links, the strength of the link between two pulsars, also the directions. Hepatic connectivity is a little bit complex matrix because it's not symmetric and it has positive and negative values. But it's really interesting to know that hepatic connectivity can be split in two different matrices. So hepatic connectivity is the multiplication of the first, and it's that one that is S. The first is functional connectivity, just a simple sample connectivity. So it's again a symmetric matrix telling us the strength of the connections. There is just only a little deviation of the symbol, because this is telling us that the functional connectivity of the states. So when we modify, we cleaned the signal from the blood source. The second one, S, is a skew matrix, as it retaining just only the information about directions. So looking here, if you want to just to start roughly 80 pulses. So you can sum row by row, and you have the strength, and you can see that we have both positive and negative values. If the sum is negative, that means that the parcel is, the parcel is roughly organized in this way. If S is positive, so this is a sync node. Sync, remember also the Valentin-Riedel publication. If S is positive, means that the parcel is mainly organized as a source node. Okay, so link, sync, and source. Okay, so a little bit complex picture, but roughly is telling us that the 5 seconds. This is the last slide, okay. A little bit complex, but it's true. I wanted to show you this. First, this one, this is really simple. You have S scores, negative, positive, and each dot is a subject. Is a sort of a summary of all the parcels that are inside that subject. And so we have an organization. We have a subject that are acting mainly with a sync. So whose parts are, acting as a sink, and it has this subject has also a low metabolic activity, while subjects having several parcels, the majority of parcels, several, more than half parcel organized in as a source, they have also, the subject has a higher glucose consumption. So this is mainly the picture, and is really sort of repetition of the results of Harrington Riddle with a little less expensive experimental setup. Okay, so what we can also learn, going the details inside, for instance, subject by subject, and trying to understand what's happening inside the networks, you have to read this. This is referring the situation of, for each network of S, so the directions. Remember, S negative, they are sink, and S positive, they are source. So this is some sense of what is happening inside that value that is just only simplification, general simplification. And there is this, we have a sort of gradient between the unimodal to transmodal networks, and the same is repeated when we order also the network by looking the detail of the metabolic consumptions. And this is what's happening when we see an opposite example, opposite subject like that one. So the meaning is we have a lot of other different results referring to the link between directions and functional connectivity with the metabolic connectivity. I think in this way we are really trying to, we are a way to enforce both information and to understand a little bit better the contribution of the metabolic of the metabolism on the structure of the brain. So of course, the brain consumes a lot of glucose, but in any case there are brain network organization that is linked to a lower consumption, so it will be more efficient in comparison to other one. So that was the last within 5 minutes, and thank you for your attention, and I finish.